왜?
Okay, guys, let's start. So, how was the exam? Eh? Any questions about the exam?
언제쯤 나와요? 아니면 답이나?
답은 이번 주 내로, 그 다음에 채점은 결과는 다음 주 내로 준비를 해볼게요. Okay, so so currently we are learning about this Gram-Schmidt process. So it's basically the process of making linearly independent vectors into a orthogonal set, right? So if they are linearly independent, there exists some non-zero angles between any two pairs of vectors, right? Something like this, right? But they are all linearly independent, so they span all the three-dimensional space, but their degree is not that not 90 degrees, right? So making them into a 90 degree and exactly orthogonal to each other between the any pair of vectors. So that's the Gram-Schmidt process. And then Gram-Schmidt process is basically like a projection of the new vectors onto the span of the previous vectors. Okay, and then we remove that orthogonal projection part, and then the remaining part will be just orthogonal part, right? So initially, these two vectors were given, and then we form this subspace. Okay, and then given this new vector, we decompose, or we just represent this x3 into these two parts. So the first one is orthogonal projection of this x3 onto this w2, which is spanned by this v1 and v2. And then this remaining part, which is purely orthogonal. So if I just move it to this vector in parallel, so that it can start with the origin. And this vector is completely orthogonal to any vector from this w2. Okay, so that was the Gram-Schmidt process, and then yeah. So in the case of V3, so initially we are given this just a linearly independent vectors, but we want to make them into a orthogonal basis or orthogonal set of vectors that spans the same subspace. So in the case of V3, from the original X3, we remove this orthogonal projection part that is spanned by the previous vectors of V1 and V2. So that was what we were doing in this Gram-Schmidt process. But in this case, we can rewrite it in this form. X3 equals V3 plus, yeah, so we basically move these two parts to the left-hand side, and then it's becoming a V3 plus V1, V1, X3, V1, and V1 plus V2, V2, X3, V2, and V2. Okay? So this is basically a linear combination of V1, V2, and V3, right? So this representation gives us the linear combination representation of the third vector from our linearly independent set, right? So we picked up x3, and then we represented it as a linear combination of orthogonal vectors that we created so far. Okay, so up to x3, we changed them into v1, v2, v3, which are all orthogonal. So x was like these, and V vectors were all orthogonal to each other. And then this equation gives us the linear combination representation of x3 in terms of these orthogonal vectors, v1, v2, and v3. Okay, and then so x3 can be represented as a linear combination. So of these v1, v2, v3. So these are long and thin column vectors. And then the linear combination coefficient is something like this. So this is A, and this is B, and C is just 1. So let's just rewrite this as A and B, and so A, B, and 1. Okay? Okay, so this is a Gram-Schmidt process, and then orthonormal basis is a simple one. Once we created this orthogonal set or orthogonal basis, and then we can just normalize each vector so that their length is 1. And then this QR factorization is it's a matrix multiplication form by using from the computation of this Gram-Schmidt process. So so we were given x1, x2, and x3. Maybe up to x4. Okay, so these are the vectors that are just linearly independent. And then we were obtaining v1, v2, v3, and v4. Okay, these are our Q. And then, in this case, in order to create x1, or in order to represent x1, this is represented as this, which is a linear combination of v1. So in terms of a linear combination coefficient, it will be 1, 0, 0, 0. And the x2 is this guy. So we just move this guy to the left hand side. So this part will be our coefficient for v1, and v2 will have a coefficient of 1. Okay. So this guy will be 1, and this part will be this part, right? Because this is a linear combination coefficient associated with the v1. Okay. So as you can see from the computation of these Gram-Schmidt process, all the diagonal components will all be just 1. Okay, and then so so those components will be some non-zero values, and then still in this part will all be 0. So that's how we obtain the upper triangular matrix, which we call R. Okay, so that's how we complete or finish this QR factorization given this matrix that has a linearly independent column. Okay, so last time one student asked, what if our matrix A has linearly dependent columns? So they are not all linearly independent. So if some of them are linearly independent, and then after this Gram-Schmidt process, suppose V3 was linearly dependent, and then this guy will be just a 0 vector, right? Because in this case, the third vector was completely inside of the span of the previous two. So after projecting them, the projection point will be just the same vector because the original vector was already inside of the span, right? So after removing this projection part, just like this. So this is removing the projection part and making the residual or remainder as the orthogonal part, right? So this orthogonal part will be always 0 in the case of V3 being linearly dependent of V1 and V2. So in this case, QR decomposition doesn't work. So in that case, we do not try to compute the QR decomposition. So just to make things easier. So we always assume that matrix A has a this n by n matrix where each column or n different columns are linearly independent. Okay, so that's a basic assumption or kind of starting assumption that makes this QR decomposition valid or interesting. Okay, and then here, yeah, so although you guys already know the span of the columns of original matrix, okay, so that was called col A, right? So column space, the span of all the columns of matrix A, so that will be the same as col of Q, right? So basically, we wanted to maintain, our intent was to maintain the same subspace spanned by the original matrix A in the case of matrix Q. Okay, so they are basically spanning the same space. Okay. Okay, let's look at the example here. So suppose we want to perform the QR decomposition on this matrix A. So we are given 3 linearly independent columns, originally in the matrix input matrix A, and then we want to create another matrix Q, which is now a orthogonal to each other. So these are V1, V2, V3, right? And then they are spanning the same space, but they are providing the orthogonal basis for the exact same subspace. Okay, so yeah, in the case of V1, they were set as the same as X1. So this one was X1, X2, X3. So we set V1 as X1, and in the case of V2, we subtract the projection of X2 onto the previous the subspace W spanned by the previous vector. So in this case, this is only spanned by the V1, right? So we can compute the remaining part by subtracting the orthogonal projection part. Okay, so this is our V2, right? Okay, and then yeah, optionally we can basically normalize this V2, the vector V2, onto this unit vector U2. Okay, so in this normalization step is really simple one. So once we obtain this as V2, and then we just scale them so that the length of the vector becomes just 1. Okay, but in this case, so if we perform the normalization, then yeah, something changes. I mean, there is something that changes, and that part is this. So back to the original Gram-Schmitt's process. So in this case, we didn't include, or we didn't perform the normalization step, right? So the direction is the only important part because we are concerned about the angle only, right? So, but yeah, just for the convenience, we want to make them to be having an equal unit length, so that the vector of the length of the vector becomes 1. So up to this point, we obtain this purely orthogonal part, right? After subtracting the projection part, and then once we normalize them so that the length of 1, and then let's see. Suppose we normalize, so this one was something like this. So it was, yeah, it was vector like this, 1 and -1. Okay, so suppose that was V2, and then if we just normalize them, then we know it's normalized as this guy, 1 over square root 2 and -1 over square root 2. And then what is the scaling factor of it? this was original V2, but we changed this V2 into U2, which is now a normalized one. So U2 is of course square root 1 over square root 2 times V2, of course, right? And so in this case, if we are going to use this U2, so this part, so let's change this guy as this one. V2 equals square root 2 times U2. Okay, so V2 becomes square root 2 U2, right? So instead of using V1 and V2 and V3 in our Q part, if we are going to use them by using U1 and U2 and U3, so U1, U2, and U3. So in this case, so if we set this guy as Q, so in this case, Q is having a really nice form. So instead of just having orthogonal vectors, we just have a orthonormal columns, orthonormal vectors. So that's just for kind of convenience. So in this case, we always saw, in these cases, these values were all ones without having any normalization. But when performing the normalization, this guy, so instead of using this, we set Q as this guy, U1, U2, U3, U4, right? So originally, in order to represent V2, the linear combination coefficient of V2 was always 1. But if we change it to U2, and then this value will become, this value will become square root 2, right? Because we scaled V1 to U2, right? And so, in order to create or generate the same vector representation or same linear combination, we can accordingly set these values on the diagonal so that the lengths of each V1 through V4, okay, in place of these diagonal positions. Okay, so back to this example, we computed V2, and then we changed it to U2. Okay, so in this case, let's see. V2 equals square root 12 times U2, okay? No, it's square root 3 over square root 12, right? So this guy was the length of this vector V2, right? So instead of seeing just 1, we see this exact scaling factor, right, in order to represent X2. Okay? So now from these representations, those two are working as linear combination coefficient, right? So in this case, so we have a Q here as U1, U2, and U3, but in the case of an R, and in the case of X2, which is corresponding to the second column of R, right? So in this case, this column will be the same as these columns, right? So still, we can see that R is an upper triangular matrix, of course, but now the diagonal part will be just a scaling factor instead of just 1, after making these U1 through U3 as a orthonormal vectors. Okay. So please don't get confused by this normalization step. This is just a simple process of making these vector lengths as 1. Okay, so for V3 for the case of V3, we perform the same thing. So altogether, yeah, we constructed Q, which has a 3 vector that are also normal to each other. So that has, each vector has a length of 1, and then they are orthogonal to each other for any pair. And then in the case of R part, yeah, this one was the linear combination coefficient by using these orthogonal vectors to represent x1, right? And then this one was coefficient to generate x2, and this part is for x3. Okay? So that is basically QR factorization. And then the last slide, yeah, so this is a little bit of a peripheral thing. So if you're given matrix A, which has a linearly independent column, so we just learned how we compute or obtain QR in this QR factorization, right? But here in this situation, which the last slide is talking about, is that suppose, yeah, so we don't want to compute QR factorization directly because someone already gave Q. So we are given A, and here the situation is that instead of asking you guys to compute QR factorization directly, I will give you just a Q matrix. Okay, so someone already computed this QR factorization on your matrix A, and then that guy gave what the Q is. Okay, and then how can we compute R? How can we compute R? So this process, so it was, yeah, in the process of QR decomposition, it was like a sequential process, or like this kind of iterative process. So we construct the first column of Q and then the first column of R to represent the x1, and then we move on to the second column, right? The second orthogonal vector Q2, no, U2, for example, yeah, because we are denoting that as a U. So U1, and we move on to the U2, and then now R2, or the second column in R, right? That corresponds to the linear combination. So we kind of proceed column by column from Q and R, right? But in this case, someone already gave Q, and then we can just omit. I mean, the purpose or our task is to compute this matrix R. But in this case, we can very easily compute this R without having to proceed by column by column. So that trick is this guy. So so Q is also, yeah, the matrix that has also normal columns. So Q was U1, U2, U3, which are all orthogonal to each other, right? And then in the case of this matrix Q, we learned that this result, I mean the product of Q transpose Q equals identity, right? So in this case, we have these column vectors, and then Q transpose Q will become I3, right? So the dimension of this identity matrix will be 3 by 3 matrix. Okay. Okay, and then let's just remind what this was. Q and Q transpose. What was it? Q transpose. Yeah, this was kind of transformation matrix that performs some function. So that is some function. So when talking about the function, yeah, so we learned something like this: A times X, yeah, which we've seen a lot. But we can view this as a function of X, right? That sends the vector X onto another vector Y, right? So that transformation is performed by this matrix A. So in this case, we treat this part as matrix A, okay? And then AX for any given vector X, this guy, or QQ transpose X, this will become the projection point or projection vector onto the subspace spanned by u1, u2, and u3. Okay, so let's see. In this figure, so if you wanted x3, okay, and then suppose I gave you the also normal vector that spans the same space of this w2, and let's call that as q. So yeah, let's call that as q2, okay, because it's corresponding to w2, and then u1, u2 is already given, okay, and then you guys know how to compute this point, which is a projection of the vector x3 onto this subspace, and then yeah, you know how to compute this guy, but alternatively that can be performed by this q transpose times x3. So that will become this point, which is also a projection of x3 onto w2. So that way, this part can be viewed as a function transformation, linear transformation of matrix A that sends any vector x3 onto its projection to this in this subspace W2. Okay, so that's really important part. So let's see. Okay, so that was kind of a side note, or something that we learned from the other chapter. But let's get back to this QR factorization example. So yeah, back to this guy. So we know this guy, Q transpose Q equals identity. So yeah, so here the task again is to compute R very easily. Okay, and then suppose A, so I'm just rewriting the QR factorization. And then here Q is given and A is given, and then if we just multiply Q transpose A, this guy, and then let's see how the right hand side expression is changing. So in this case, I multiplied on the left with the Q transpose, and the A is the same as QR, and then Q transpose Q becomes identity, right? So that will only leave us with this matrix R. Okay, so we can just simply perform Q transpose A. Yeah, we can perform that, and then that will give you the matrix R. 요거요? 요거 두 개? 네, 요거 두 개 뭐요? 네네네. 이거요. 네. 일단은 이 어떤 벡터가 주어졌을 때 이거를 그 우리의 subspace로 subspace로 프로젝션 하는 거, orthogonal 프로젝션 하는 거 우리 알잖아요. 어떻게 하냐? 만약에 어떤 orthogonal 베이시스 벡터가 두 개가 주어졌어요. 그리고 그게 뭐 예를 들면 u1과 u2라고 해요. 그러면 어떻게 해요? 요거 내적해서, 네? 뭐 그 맨날 나오는 식 있죠. 뭐 u1 곱하기 u1 한 다음에 x3 내적을 이렇게 한 다음에 그 다음에 u1 이 방향 벡터를 곱해주잖아요. 그죠? 이렇게 하고 또 뭐죠? 또 플러스 해갖고 두 번째 벡터 또 해갖고 이게 그게 되는 거잖아요. 그죠? 네, 그 다음엔 뭐 똑같은 얘기인데, 근데 이제 우리의 벡터, 우리의 베이시스 벡터가 also normal이라고 하면 이놈이 없어져요. 깔끔하게. 그죠? 깔끔하게 없어지고, 그 다음엔 이거를 어떻게 쓸 수가 있느냐? 가만히 있어보자. 네, 이 내적을 어떻게 쓸 수 있냐면 u1 transpose x3라고 쓸 수가 있어요. 그죠? 이건 상수고 여기에 u1이 이렇게 곱해지는 거죠. 이게 방향을 나타내는 벡터. 근데 지금 여기 상황은 이게 길이가 다 1인 거예요. 그죠? 이거 그냥 다시 쓰면 어떻게 되냐면, 네, 그럼 하나 더 써볼게요. 두 번째 거 u2 transpose x3 그리고 이게 u2 이렇게 되겠죠. 그죠? 그러면 이거는 어떻게 나타낼 수가 있냐? U1, U2 이 매트릭스에다가 곱하기 벡터 X3를 이렇게 곱한 것과 네. 여기다가 이제 U1 트랜스포즈, U2 트랜스포즈 그 다음에 이제 벡터 X3 이렇게 쓴 거. 즉 그 말은 이게 Q 트랜스포즈 X가 된다는 거. 이거를 이 식을 이렇게 매트릭스 형태로 리어레인지를 할 수가 있었다라는 거죠. 네, 어떻게 되는 거냐면 이게 다시 한번 설명을 하면, so yeah, this is basically what we learned when understanding this Q transpose X will become the orthogonal projection when given the also normal vectors for our basis. Okay, so in this case we know or we understand this is the expression for the orthogonal projection. But once you arrange them as the matrix multiplication thing, and then you obtain or you will see this guy is exactly the same as Q transpose and the vector X. And then in this case, yeah, we can view that in this form. So in this case, it's a linear combination of U1 and U2. Then this guy is a linear combination coefficient, right? So U1 and U2 is our matrix like A. Okay, so we know AX is a linear combination of the columns of an A, A1, A2, A3, and X is a vector that has a scalar of X1, X2, X3. And then you guys know this is a linear combination of A1, A2, A3 that has the coefficient of X1, X2, X3 respectively, right? So we can view this guy in this matrix vector form. So in the matrix on the left, that matrix should have our vector, okay? And then this part should be our linear combination coefficient, U1 transpose X3, U2 transpose X3, right? So this is just a scalar, which is exactly like this guy, X1 and X2, right? But this part can further be written as U1 transpose, U2 transpose times X. Okay? So this part can be written as Q transpose and X. And then what was this? This was Q, right? So Q transpose X. And that way we obtain this. But so this will become A, and this guy will become the something like X. That gives us the linear combination coefficient. But if we view them in this manner, so Q transpose is a one matrix, okay? So that can be viewed as a function or the linear transformation that changes or sends the vector X or this vector X3 to this orthogonal projection. Okay?
그 마지막에 그 R은 Q 트랜스포즈 A에다 Q 곱한다는 거 QR이 A니까 똑같이 그냥 프로젝션에서 여기로 원래
여기서는 뭐 프로젝션 그러니까 이게 A가 QR이니까 여기다가 Q가 주어졌다고 했을 때 Q 트랜스포즈를 한번 곱해보자 이거죠. 아이고. 네. 여기서 이제 Q 트랜스포즈를 A에다가 이렇게 곱해본다면 Q 트랜스포즈 Q 그다음에 R 이렇게 되고 Q 트랜스포즈 Q는 아이덴티티 매트릭스가 되잖아요, 그죠? 왜냐하면 also normal 컬럼들을 갖고 있는 매트릭스이기 때문에. 네, 그러니까 이제 R만 남고 결국은 R이 Q 트랜스포즈 A라는 뜻이죠. 되게 쉬운 건데. 근데 okay, so this is really simple manipulation, right? By utilizing this factor of Q transpose Q equals identity. But let's look at this representation a little bit more carefully. So what was R? What was R? So R was, yeah, the information shown in R. I mean, each column of R is the linear combination coefficient of this basis vectors contained in Q in order to represent each vector that we have in A, right? So back to this A equals QR, so we are given Q, which has like a 3 vector, for example, Q, U1, U2, U3. And what was R? What was the meaning of R? So the first column of R was the linear combination coefficient to represent this input, the first column in the input matrix A, right? Okay, so that was the interpretation or kind of meaning of R, right? And then here is, so yeah. So we have Q, right? So you guys know, yeah, so we learned that this Q transpose is a kind of a linear transformation that performs just the orthogonal projection, right? But when learning it, when studying it, this part was what? The linear combination coefficients, right? As we just saw in the previous figures, and right. So this guy is a linear combination coefficient, okay? And so so given A and given Q, we want to obtain R, and the meaning of R is the linear combination coefficient, right? And then that linear combination coefficient, for example, like the first column of R. So R1, for example, this R1 is corresponding to this part, right? So this part will become Q transpose, and what is the input vector? That input vector will be A1, because we want to represent, so A has like 3 columns, and then we want to first represent this first column A1, right, into a linear combination of the columns in Q, right? And then Q transpose X in this expression. Q transpose X part was our linear combination coefficient part, right? So Q transpose A1, because our input vector was A1. So this guy will be exactly the same as this first column of R, right? Because the meaning of R is containing this, or that is corresponding to the linear combination coefficient, right? And then what about the second column? It's like a Q transpose times A2, because now the input vector becomes A2, right? So that way, this part can be written as this guy. So R1 is nothing but Q transpose A1, because we are already given this Q, right? And then the second one is second column of R will become Q transpose A2, okay? And then this guy can be written as Q transpose A, which has the column of A1, A2, and so on, okay? So this is kind of a mechanical, or yeah, it's involving really simple manipulation. But if you're gonna just apply this formula, and then this is just a mechanical kind of application of this formula without too much of a kind of understanding, but you can understand intuitively about what this should be the same as R. Okay.
그래프미츠 프로세스를 통해서 큐를 구했잖아요. 그런 것도 부분이 있는데 그냥 위에 부분을 베시스를 준 다음에 그걸 갖고서는 R을 빼고 N은 QR 그냥 서브 그걸 QR 트랜스포메이션을 쓸 수 있는
예, 그렇죠. 그러니까 사실 이게 그러니까 Q가 먼저 주어지고 그 다음에 R을 이렇게 구하는 게 조금은 그 그램-슈미치 프로세스랑은 조금 안 맞아요, 순서가. 그램-슈미치는 아까도 얘기했듯이 순서들이 이게 이렇게 구하는 게 우리가 하는 일이거든요. 근데 이거는 그러니까 좀 어떤 스페셜 케이스에 대해서는 우리 매트리스 A가 있고 Q가 이렇게 쓱 주어진다고요. 네, Q가 이렇게 싹 주어졌을 때 그러면 R을 그냥 간단하게 구할 수 있는 방법으로서 이런 방법을 생각을 해볼 수가 있다는 거고요. 이거에 대한 어떤 실질적인, 이게 실제로 그러면 Q가 언제, 그러면은 R 없이 Q만 먼저 딱 주어질 때는 언제냐? 네, 그거는 뭐 그냥 그런 상황이 있을 수 있다라고 정도로 이해를 하고 넘어가는 게 좋을 것 같아요. 네. 다만 이렇게 어떤 also no 그러니까 이거는 기본적으로 그 also normal columns, 그러니까 Q가 있을 때, 그 Q에 also normal column들이 있을 때 그 스페이스로 누군가를 프로젝션을 하고 싶어요. 그러면은 그게 매트릭스, 그러니까 매트릭스는 그 인풋 매트릭스 A가 지금 이렇게 여러 개의 인풋 벡터들로 구성이 되어 있을 때 얘네들에 대해서 그 리니어 컨비네이션 코에피션트, 그러니까 프로젝션 했을 때 그 포인트에 대한 리니어 컨비네이션 그 코에피션트를 구하고 싶다. 그럼 뭐 그냥 Q 트랜스포즈 A 하면 된다는 거예요. 이게 실제로 굉장히 많이 쓰여요. 네. 예를 들면 네. 이게 하여튼 뭐 되게 중요해요. 그러니까 뭐 우리의 데이터 아이템이 그 머신러닝, 데이터 마이닝, 뭐 기계학습, 인공지능 다 이런 거 해서 이렇게 데이터 아이템이 이렇게 인풋 벡터들에 이렇게 쭉 하이 디멘저널 레프레젠테이션으로 주어져요. 그래서 우리는 뭐 맨날 방정식만 풀고 있지만 이번에는 세팅이 뭐가 되냐면 요거 하나하나가 예를 들면 한 사람 한 사람의 환자의 어떤 DNA 기록, 그럼 그 DNA 기록이 쭈르륵 어떤 형태의 벡터로 나타내지고요. 이 DNA 기록에 대한 이 디멘전, 그러니까 이게 디멘전 1, 디멘전 2 이렇게 되는 거예요. 그러니까 이게 뭐 예를 들면 사람을 나타낸다. 그럼 이게 사람의 키, 몸무게, 그 다음에 또 뭐가 있을까? 눈의 색깔, 뭐 남자, 여자, 성별 이런 다양한 정보들을 포함을 하고 있는 형태의 어떤 하나의 벡터들로 각각의 데이터 아이템들이 나타내지고요. 근데 이 보통 디멘전들이 굉장히 커요. 이게 뭐 한 10, 100, 1000, 만, 100만, 1000만, 뭐 밀리언 쉽게 넘어가요. 진짜 쉽게 넘어가요. 그러면 이걸 그냥 고지고대로 이걸 그대로 처리하면 너무 힘들어서 무슨 짓을 하냐 하면 기본적으로 좀 의미 있는 Q를 찾아요. Q를 찾는다는 거는 이게 디멘전이 뭐 100개가 있다고 해봐요. 그럼 얘 벡터들은 100디멘전에 살고 있는 애들인데 얘네들이 예를 들어서 한 100디멘전 스페이스고 여기에 5차원 정도의 어떤 우리한테 굉장히 유용한 그런 서브스페이스가 있어요. 그 5차원은 예를 들면 우리가 이게 예를 들면 이 사람이 어떤 특정 질병을 갖고 있냐 아니냐, 어떤 특정 암이냐 아니냐. 그럼 봐봐요. 키나 몸무게가 사실 암에 영향을 미칠까요? 뭐 미칠 수도 있겠죠. 근데 뭐 사실 키 크다고 그래요. 키는 사실 뭐 그렇잖아요. 키 작다고 암 더 걸리는 건 아니겠죠. 예. 그럼 걔네들은 사실 그 디멘전은 실제로 빠지는 게 맞거든요. 이거 할 때는. 근데 그거를 그냥 기계적으로 그냥 그 디멘전을 그냥 하나하나 따로따로 빼는 작업을 하는 게 아니라 얘네들 간의 어떤 서로 간의 그런 어떤 코릴레이션이라든가 이런 말 그대로 진짜 좀 이 암 진단에 도움이 되는 서브스페이스가 존재해요. 그리고 그 서브스페이스는 이 100디멘전에 비해서 훨씬 더 작아요. 그 디멘전이 예를 들어서 한 5디멘전이라고 해보세요. 그리고 그 5디멘전을 누가 하여튼 구해줬어. 그리고 이 5디멘전에 대해서 이 5디멘전에 해당하는 그 베이시스들을 우리가 그램-슈미치 프로세스를 구해서 Q를 구했어요. 그러면 이 5디멘전으로 어떤 사람의 이 100디멘전의 벡터든 다 갖고 오면 Q 트랜스포즈 A, 그러니까 어떤 사람의 벡터예요, 이게? 100디멘전의 벡터. 우리는 Q만 있으면은 Q 트랜스포즈 한 다음에 그냥 A만 곱하면 이거는 바로 이 암 진단에 유용한 이 5디멘저널 서브스페이스로 얘네들을 매핑을 하게 되는 거예요. 네. 그래서 그 5디멘저널 벡터를 가지고 실제로 암 진단을 하게 되는 거죠. 네. 그런 측면에서 이제 이런 Q라는 게 따로 이렇게 구해지는 그런 상황들이 꽤나 자주 발생해요. 네.
저희 느끼는 거는 베이시스
네, 그러니까 베이시스는 그러니까 이렇게 생각해 볼 수가 있어요. 예를 들면 이런 경우들이 발생해요. 그러니까 디멘전은 100인데 샘플 수 혹은 우리가 모아놓은 사람 수는 한 15명밖에 안 돼요. 뭐 예를 들면 희귀병 이런 것들은 샘플 하나 수집하는, 그러니까 사람 그런 환자를 한 명의 정보를 수집하는 것도 굉장히 비싸고요. 뭐 그렇잖아요, 그죠? 그리고 그 사람이 실제로 그 병이냐 아니냐를 진단을 해야 그 정보까지 우리가 얻게 되고요. 그런 측면에서 이렇게 되면 사실 디멘전은 100인데 우리의 벡터 A는 15개의 컬럼밖에 없어요. 그럼 얘네들이 실제로 이 모든 데이터 아이템들이 그러니까 얘네들이 살고 있는 서브스페이스도 역시 15디멘전밖에 안 돼요. 그렇죠? 그러니까 100개 서로 다른 우리가 100가지 종류로 어떤 사람들을 나타내고는 있지만 얘네들이 실제로 살고 있는 서브스페이스는 15디멘전밖에 안 되는 거예요. 그죠? 근데 지금 여기서 얘기하는 거는 예를 들면은 뭐 이런 경우도 있을 수 있고요. 근데 이게 예를 들면 한 뭐 10,000사람쯤 돼요. 그러면 10,000사람은 얘네들이 적당히 리니얼리 인디펜던트 하다면 뭐 이거 똑같은 거 뭐 하는 거예요. 그래서 이 100디멘전을 풀리 다 스팬을 할 수가 있겠죠. 그죠? 뭐 그렇다고 그럴 경우가 많겠죠. 그죠? 그런 경우에도 실제로 어떤 방향들은 그러니까 이 방향들은 어떻게 결정이 되냐면 그러니까 예를 들어서 방향을 우리가 찾고 그 방향을 랭킹을 소트를 한다고 생각해 보세요. 그 소트를 하는 기준은 뭐냐면 암 진단에 도움이 되는 방향으로 소팅을 하는 거예요. 그러면 이 3디멘전 스페이스에서도 어떤 방향이 과연 암 진단에 가장 도움이 되는 방향일까를 하나 딱 찾아요. 네. 그 다음엔 두 번째 방향을 찾는데 두 번째 방향은 얘 무조건 수직이 되게 찾는 거예요. 수직이 되게 찾되 두 번째로 가장 암 진단을 잘하는 벡터를 또 찾아요. 네. 그리고 세 번째 디멘전을 보니까 얘는 추가를 했더니 그러니까 이 실제로 우리 데이터가 살고 있는 서브스페이스에 포함된 세 번째 디멘전이긴 한데 3등부터는 오히려 그 암 진단에 도움이 되기는커녕 얘는 방해만 해요. 그런 디멘전이 실제로 존재해요. 그럼 얘는 없으니만 못한 거거든요. 얘를 오히려 이 정보를 우리가 빼버렸을 때 암 진단을 더 잘할 수 있어요. 네. 그렇게 되면 결국은 얘네들이 살고 있는 서브스페이스가 원래 100디멘전 다 풀리 스팬하고 있었지만 실제로는 두 개의 디멘전만으로 혹은 두 개의 디멘전으로 이루어진 이 서브스페이스에다가 프로젝션을 한 그 어떤 새로운 점들 혹은 그 새로운 벡터들을 그거를 어떤 암 진단에 사용을 하는 게 훨씬 더 도움이 될 거라는 거죠. 그렇게 되면 결국은 이게 디멘전 리덕션이라고 부르고 크게 뭐 다 딥러닝 이런 것도 디멘전 리덕션 잘하는 거예요. 그게 디멘전 리덕션. 네, 그래서 디멘전 리덕션, 그러니까 디멘전을 줄인다는 의미로도 볼 수가 있지만 이거를 어떤 데이터의 트랜스포메이션이라고 볼 수 있어요. 아까도 프로젝션도 트랜스포메이션이라고 얘기를 했잖아요. 그리고 여기서 프로젝션은 우리가 그 전에 배운 그러니까 프로젝션도 이런 게 있었잖아요. A가 이렇게 생겨 먹으면 이거는 X 벡터가 뭐 예를 들어서 5디멘전이다. 그러면 뭐 예를 들어서 여기가 12디멘전이다. 그럼 이거는 5디멘전al 벡터를 12디멘전 벡터로 바꿔주는 트랜스포메이션이고 거꾸로 매트릭스가 이렇게 좀 이렇게 뚱뚱하게 생겼어요. 여기가 5, 12 이러면 여기 12디멘전al 벡터를 갖다가 트랜스포메이션을 하면 이거는 5디멘전al 벡터로 옮겨와요. 네, 그래서 이런 식으로 디멘전이 줄거나 늘거나 하는 이런 어떤 특성이 있잖아요. 근데 이 디멘전을 보통은 줄여요. 늘리는 거는 썩 그다지 늘리기도 해요. 그 어떤 조건을 가지고 늘리고 이제 뭐 그거를 이야기하기로는 그걸 이제 스펄스 코딩이라고 이제 이야기를 하는데 코딩이라는 말은 코딩이 결국 트랜스포메이션이에요. 이 어떤 벡터를 또 다른 벡터 형태로 코딩을 시킨다. 그러니까 이런 프로그램 코딩이 아니라 유전자 코드 뭐 이런 새로운 표현을 찾는다. 새로운 벡터 레프레젠테이션을 찾는다라는 걸 코딩이라는 말을 쓰고요. 다시 원래대로 돌아와서 여기서 이제 100디멘저널 스페이스에 살고 있는 벡터, 각각의 사람들의 벡터를 예를 들어서 아까도 얘기했듯이 암 진단에 연관이 되는 도움이 되는 디멘전은 딱 2개밖에 없다면 혹은 그 2개의 베이시스로 이루어진 서브스페이스만 도움이 된다면 이거를 그런 서브스페이스를 찾은 그 서브스페이스의 베이시스를 찾되 그 올소고널 베이시스를 찾는 거예요. 똑같아요. 그램 슈미츠 써갖고 올소고널 프로젝트 그걸 올소고널 베이시스를 찾아요. 그 똑같은 서브스페이스를 스팬하도록 하는. 그러면 결국 그 스페이스로 프로젝션을 한 포인트는 어떻게 구하느냐? 결국 Q 트랜스포즈 어떤 벡터 X가 있을 때 X 이런 식으로 구한다는 거예요. 이런 식으로 구하면 우리가 Q만 구해놓으면 어떤 새로운 환자가 딱 들어왔어요. 걔에 대한 100디멘전al 레프레젠테이션이 있어요. 그러면 그 Q 트랜스포즈 바로 곱해버리면 걔가 암 진단에 도움이 되는 스페이스로 쫙 이사를 오는 거예요. 그 다음에 참고로 이제 딥러닝 많이 들어봤잖아요. 그죠? 딥러닝은 뭐 하는 거냐? 이렇게 딱 디멘전을 줄여요. 디멘전을 2디멘전으로 딱 줄여요. 여기다가 하나만 더요. 하나만 더요. 난리니어 트랜스포메이션을 하나만 더요. 그 말은 무슨 소리냐면 시그모이드 펑션 이런 거 혹시 들어봤나요? 렐루, 10H, 소프트맥스. 네. 시그모이드 펑션이 대충 요렇게럼 생겼어요. 요렇게럼. 네. 그래서 이 리니어 트랜스포메이션을 하면 예를 들어서 100디멘전에서 2디멘전al 벡터로 바꿔놨어요. 근데 이 리니어 트랜스포메이션이라는 건 약간의 한계가 있어요. 약간의 한계. 그래서 요거를 살짝 보정을 해줘요. 어떻게 보정을 하냐면 예를 들어서 뭐 2, 100 이런 거는 한 2, 한 15쪽으로 바꿔줘요. 즉 너무 큰 애들은 리니어는 큰 애들을 그냥 크게 만들어버려요. 근데 실제로 이게 뭐 암 진단이다 이런 어떤 기냐 아니냐를 판단할 때는 이게 숫자가 너무 그러니까 선형 변화는 이 숫자 큰 숫자는 그대로 큰 숫자로밖에 나타낼 수가 그렇게밖에 못해요. 그러면 이게 뒤에 가서 좀 이게 진단을 할 때 이게 헷갈려져 버리거든요. 그래서 큰 놈을 이렇게 적당히 좀 줄이는 거예요. 뭐 로그 변환 같은 거 있잖아요. 로그 뭐 한 100만 10의 6승 그럼 6밖에 안 나오죠. 그죠? 이렇게 플랫하게 되잖아요. 플랫하게. 그죠? 그러니까 로그는 좀 좋진 않은 게 마이너스는 도메인 마이너스 값은 로그 값이 없잖아요. 정의가 안 되고 또 0에 가까우면 가까울수록 거꾸로 이게 굉장히 기울기가 스티프해지죠. 그러니까 0.1, 0.01 이렇게 되면 값은 차이가 얼마 안 나는데 마이너스 1에서 마이너스 2로 빵 뛰죠. 그럼 0.0000001 이거 뭐 얼마 차이가 나겠어요? 0.01이랑 뭐 요만큼 차이인데 근데 값은 마이너스 뭐 한 뭐 1000, 100, 만, 10만 뭐 이렇게 가잖아요. 그러니까 이렇게 더 센서티브하게 만들어버려요. 뭔가 증폭을 시켜버리거든요. 증폭은 별로 안 좋아. 네, 증폭은 별로 안 좋아요. 그래서 저쪽 뒤로 가서 마이너스 쪽에서도 우리가 정의가 되고 어떤 변환이 정의가 되고 또 그쪽에서도 이런 어테뉴에이트를 할 수가 있게. 그러니까 즉 2,100이 2,15로 되고 또 2, 예를 들면 마이너스 100도 2, 마이너스 15 정도로 바꿔주는 어떤 변환을 생각하면 그 변환이 이렇게 생긴 거라 이거죠. 이게 이제 100일 때 얘가 한 뭐 예를 들면 이 함수 값은 한 15쯤 되는 거예요. 네. 네. 이런 식으로 변환을 시켜서 이런 변환을 하나 싹 끼면 선형 변환 한 다음에 이걸 하나를 싹 껴요. 그 다음에 이런 선형 변환을 여러 개를 만들어요. 그러니까 뉴럴넷 뭐 대충 뉴럴넷 뭐 뻔하죠. 뭐 이렇게 막 돼 있죠. 점들 막 많잖아요. 뉴럴넷 보면. 그래서 막 이게 막 얽히고 설키고 뭐 이렇게 돼 있잖아요. 이게 뭐냐? 이게 100디멘전al 벡터예요. 그리고 이게 우리의 2디멘전al 벡터가 돼요. 그러니까 우리가 그 also subspace 그 변환을 통해서 2디멘전al 벡터로 프로젝션을 하고 그 다음에 아까 얘기했듯이 살짝 낀 그 비선형 혹은 요놈 요 프로세스가 하나 딱 껴요. 그 다음엔 그래서 나온 여기 요거 하나 없다고 하죠. 2, 마이너스 15가 있었다. 어떤 환자에 대해서 100디멘전al 환자의 그 표현 그 벡터를 넣었더니 그럼 여기서 나온 2, 마이너스 15를 또 한 번 선형 변환을 또 해요. 그 다음 레이어로 옮기기 위해서. 그럼 이거는 뭐 저기 디멘전이 커졌으니까 이 경우는 이제 뭐 아까는 디멘전 크게 만드는 게 의미는 없다고 했지만 이거 뉴런넷은 굉장히 이제 플렉서블해요. 그래서 어떤 그렇지만 디멘전이 커지긴 했지만 결국은 선형 변환은 또 똑같이 한 거고요. 그 선형 변환에다가 한번 싹 난리니어 트랜스포메이션 요놈 별것도 아닌 것 같아 보이는 요놈을 한번 싹 하고 이것들을 여러 개를 짝짝짝 쌓으니까 이 암 진단이 놀랍게도 막 엄청나게 잘 되고 엄청난 일들을 하는 거죠. 딱 요거예요. 딱 요거. 딥러닝이 딱 요거예요. 그렇기 때문에 기본적으로 지금 하는 게 되게 중요하다. 농담이에요. 진짜. Okay, so this was a little bit of an off topic. So I think I covered entirely on this QR factorization. Okay, so we now move on to the next chapter. Okay, so this least square. So orthogonality is orthogonality, but this least square is really important part. Okay, so this is actually really the most beautiful flower of a linear algebra. Okay, the reason for it is because this is actually used in, for example, like deep learning that I just described. Okay, and also many other things. Okay, so I can guarantee that you will see this kind of least square at least 3 times more throughout your undergrad study. So while you study in this university, you will hear and study this linear least squares in at least 3 different or 3 other classes. Okay, so once you learn it in this class properly, and then your life will get much easier. Okay. But this least square is really just a really small extension from this kind of orthogonal projection. Okay, so this is basically like an orthogonal projection, but we view this problem from a slightly different angle. Okay, so here the problem is something like this. So so we are given this A, matrix A, which has the size of an m by n, and also we are given this B. So this is just a simple setting of Ax equals B. Okay, I think I briefly mentioned about it, but here previously we considered whether this guy has a solution or not, right? So whether there exists a solution or not. So that is determined based on whether this B is inside of the span of the column space of an A. Right, but if B is outside of the column space, and then we conclude that we have no solution for this linear system, right? But in this case, we change or relax this guy into this form. Ax is approximately equal to B. Okay, so even when the B is outside of our span, I mean the column space of an A. So B is outside of the column space, right? But still, we can kind of compute or solve this system approximately. Okay, so the idea is really simple. So here, so we are given A and B, of course, right? And let's consider the column space of an A. So that is this kind of a plane. And then the situation here is that B is outside of our column space, right? Okay, and then what is the meaning of like solving this system approximately? So where is this approximation coming from? That approximation is actually coming from the orthogonal projection of B onto this subspace. Okay, so B is outside, so we cannot obtain the solution, right? But we can approximate this B onto some vector which is now inside of our column space. Okay, and then which point should be the approximate point of that point? Intuitively, the smallest distance, the one that has the smallest distance from that original point, that will be kind of a best approximation of that point, right? But here, this approximation, I mean, the role or the reason for doing this approximation is because now this approximated point is completely inside of the column space, right? So that's the reason or the meaning of doing this process, right? Okay, so and also that approximation that has the smallest distance. So that is the same as the orthogonal projection, right? So when we perform this orthogonal projection, the distance between the original point and the projection point, this distance will be the smallest than any other points in this subspace, right? So if we pick up another point that is inside of our column space, and then if we consider the distance from that point to the original point, this distance will be always larger than the distance from the original point and the orthogonal projection point, right? So orthogonal projection provide us with the best approximation of the B, which is outside of a column space of an A. Okay. Okay. So if we consider the orthogonal projection of B onto this column space of an A, let's call that as B hat. Okay. So previously ax equals b didn't have solution, right? Because b was outside of column space of A. So, but if we consider this approximated version of the linear system, where we approximated b into b hat. Okay, so b hat is proj and call A of B, right? So this is just a notation of that means the orthogonal projection of B onto this subspace. Okay. So once we change B into this B hat, and then this linear system will definitely have a solution, right? Because we change it B to another point that's inside of a column space of an A for sure. Okay. So solving this approximated version of the linear system and then obtaining this guy x. Okay. So this is called the solution for linear least square problem. Okay. So this guy can be viewed as the approximate solution for this original linear system, which originally didn't have any solution. Okay, and then this least squares. Yeah, let's understand why this is called a least squares. 네.
저거는 이제 지금 천연분한 x가 더큰 기회좀
그렇진 않아요. 그러니까 왜냐하면 A가 지금 이렇게 생길 수도 있고 A가 이렇게 생길 수도 있어요. 그죠?
A가 이렇게 생기면
어떻게요? 이렇게
길게
저기 뚱뚱하게 요거 연놈일 때는 뭐가 어떻게 되냐고요? 네, 아 저거 네, 그래요. 네, 좋은 질문이에요. Okay, so the question is, what if our matrix A? So yeah, let's call we have many vectors. For example, 1, 2, 3, 4, 5, 6. So we have 6 column vectors, but they are living in like a 3-dimensional space, right? So in most of the cases, I mean, generally these 6 column vectors will completely span, entirely span the 3-dimensional space, right? So yeah, that's not guaranteed, but that will be often the case, right? So in this case, our column space of A will be the same as the universe or the entire R3. Okay, so in this case, so any B will be already inside of the column space, right? So in that case, this original linear system will always have a solution, because and then also this is not a special case. In this case, we can still view or apply the same kind of process of our understanding. So suppose we have a point B, and then if we consider its projection onto the column space, but our columns this B is already inside of our column space, right? And in this case, the projection point will be remain the same, right? So even after doing the projection will have no effect. It will not change the original B, right? Even after approximating it, or even after we project it onto the column space of an A. So in this case, this guy and this guy will be exactly the same linear system, because this B and its projected vector B hat will be exactly the same, right? See. Okay, so let's understand why this is called a least square problem. So in this case, we change this guy into this form. And then here in this case, let's call the solution for this approximated version x x as x hat. Okay. Yeah. So by solving this linear system, that definitely have a solution, and that solution for this vector x, we call that vector particularly as x hat. Okay. So in this case, we can rewrite it as this guy. Okay. So among many possible x, this x hat is the solution for this approximated version of the linear system. Okay. Okay. And then let's consider let's consider this kind of problem. So b minus ax, and that is, so this is actually called a least square problem, because least means minimum, right? So that minimum is coming from here, minimize thing. So we want to minimize this guy, and then this guy is not new thing. So this is, so what is ax? What is ax? So ax is basically, so given whatever x, ax is just a linear combination of the columns of an A, right? That has a linear combination coefficient in our vector x. So ax is basically the vector inside of our column space, right? We can represent any vector in this column space. That can be represented as ax. I mean, that will have some linear combination coefficient that will form our x. Okay, and then what is this? This is So in this case, I think I already explained most of them. But let's suppose that ax. Okay, so ax was this point. Okay, and then what is the vector of b minus ax? That will be this guy, right? So b minus this vector, right? And then we have an operator of this guy, double bars. So that is representing the length of the vector, right? So basically the length of this vector. And what was the meaning of this vector? This vector was representing the difference of b and some approximated version of b, right? And then in this problem, we want to minimize the length of that difference vector, right? So this optimization problem will give you, so from that problem, so it's not originally like a linear system, right? So I want to, I ask you to minimize the difference between b minus ax, and then I want you to give the vector x that will minimize the length of this guy. Okay, and then it's really the same thing. And then where should this ax be? Okay, where should this ax in this column space of an A? And that will, you guys know, that should be the orthogonal projection of B onto this guy, right? And then the linear combination coefficient that will represent this point, right, will exist, and that is this x hat, right? So the solution for this guy will be x hat. So that means if we use this x hat in this place, and then the length of this vector will be smaller than any other cases. I mean, smaller than any other cases where we use any other vector x, right? So if we're going to use any other linear combination coefficient for in the place of an x, and then the length of this difference vector will always be larger than this orthogonal projection one. Okay. Okay, and then let's study how we can compute this x hat. Okay, let's study how we can obtain this x hat. Okay, that minimizes this difference, the length of the difference vector. So in this figure, this guy is x hat. This guy is a times x hat, right? And then we know from this figure b minus ax hat, which is this vector. So this vector is the difference from this orthogonal projection, and that vector should be perpendicular to any vector from column space of an A, right? So that's the kind of a characteristic or the meaning of this orthogonal projection. Okay, and so I'm gonna just perform. So in A, so there are so many vectors. So A was suppose A had a 3 vector of A1, A2, and A3. So the span of the columns of A will be represented as this one. So CA1 plus C1A1, C2A2 plus C3A3. So it's just a linear combination that represents one vector belonging to the span of A1, A2, and A3, right? So among many choices, the simplest choice will be, this vector should be perpendicular to any vectors that are represented in this form, right? But the simplest one will be A1, right? And A2, and A3, right? So all those inner product with this difference vector and A1, A2, A3, and this is an inner product, of course, and that should be all zeros, right? Okay, and then I'm gonna rewrite it in this form instead of using this inner product operator. I'm gonna just use this transpose version. Okay, and then this guy can be written as this form: A1 transpose, A2 transpose, A3 transpose. So I'm gonna just form this matrix which has this row vector, okay, times b minus ax hat. Okay, that will be this guy times this guy. So this is a column vector, right? As a whole, and then that will give the this inner product value, and that inner product value will become 0, and it will be, form 0, 0. This vector of 0 that has 3 zeros inside in this vector, right? And then this guy can be represented as A transpose b minus a x hat equals 0. This okay. It was from here. Okay, so in this case, I'm gonna just distribute it this way. Okay, and then this guy. Okay, this guy is called the normal equation, and how you compute x hat is actually solving this linear system. Okay, so now we obtain the new linear system where A and B are known. So this is a one vector, and this guy is now A transpose A is working as a new kind of A, and this guy is kind of a vector x that we have to obtain or solve, right? So this is a new linear system that will give you the least square solution, or this kind of orthogonal projection and its linear combination coefficient. Okay, so we'll continue next time. Okay, thank you very much.
아니 이게 저거 쓰는 게 좀 근접한 방식인 것 같아요.
네,
아까 이렇게 기분이요.
네.
이거 사면은 지속이 불러서 지속이 그러면은 이제 이건 무조건 생각이 나죠.
그러니까 피벗이
있으면
네, 이 로우에다 P1이 있으면은 지열 증가. 그러니까 이 2디멘전을 모두 다 스팬을 하면 솔루션이 언제나 있어요.
그러니까 그럼 프로젝션 할 필요가 없다.
프로젝션 할 필요가 없는 것도 많죠.
프로젝션 하는 게 자기잖아.
그렇죠. 그러니까 이렇게 그러니까 어떤 벡터든 간에 그러니까 이 스토리가 이래요. 그러니까 어떤 벡터든 간에 이제는 이게 이 컬럼 스페이스의 바깥에 있든 안쪽에 있든 나는 신경 안 쓰겠다 이거. 어쨌건 간에 그거를 바깥에 있든 안쪽에 있든 그거를 프로젝션을 한번 해주면 그 다음에 이게 무조건 안으로 들어오죠. 근데 원래 이게 안에 있었으면 프로젝션을 해도 그 똑같은 벡터로 여전히 남아 있을 거예요. 그죠? 어쨌건 그런 프로젝션을 한번 했고 그러면 그 프로젝션 한 버전의 리니어 시스템은 언제나 솔루션을 가져요. 그리고 그거를 풀면은 이게 솔루션이 되고 이게 원래 인사이드 그러니까 컬럼 스페이스 안에 있었으면 그게 이그젝 솔루션을 주고요. 그렇지 않고 바깥에 있었으면 그게 어프락시메이트한 버전의 솔루션을 준다. 네.
Last time I have submitted my homework, but this time I have no points.
Really?
Yeah. And the last time I also didn't get back my homework.
그거를 써먹을 수가
아, 근데
있는데.
이제 이
네.
공식은 올토나 그냥 베이스 쓰기만 하면은 훨씬 그 차이에요.
그렇죠. 그러니까 지금은 올소건을 하지는 아직 않아요. A가. 그죠? 그래서 이제 나중에 조금 지나면 배우겠지만 그걸 올소건을 하게 만드는 QR 팩토라이제이션을 하면
네.
A 이꼴 QR을 구하면 저 리스크의 솔루션이 굉장히 쉽게 나와버려요. 네.
지금 이 상황에서는 그냥 큐 없이 그냥 베이시스만 가지고 할 수 있는.
일단은 개념적으로 이렇다라는 걸 설명을 하고 좀